Let's talk about thin film interference. Before watching this video, I suggest that you review the video called Interference. Interference of light can be seen in many everyday phenomena such as the bright colors reflected from the soap bubbles, CDs, or thin oil or gasoline film on water. In all these and more other cases, colors are a result of constructive interference. So this constructive interference happens between the light reflected of the two surfaces of the thin film. To see how thin film interference happens, let's consider a smooth, uniform, thin, flat film of, let's say, gasoline with the thickness of T. When the light shines on the upper surface of the thin film, it will partly reflect and partly transmit it through the upper surface and partly reflect it again from the lower surface. Something like that. So this is a partly transmitted and reflected back. So we have two waves, 1 and 2, that will interfere with each other. Well, these 1 and 2 waves will come together, and depending on the phase difference, they will either interfere constructively or destructively. Now, of course, you have a question, how does it happen, the phase difference? Let's try to understand that now. First of all, let's mention that different colors have different wavelengths, so the interference may be constructive for some colors and destructive for others. That's why we see colored patterns in this picture. The destructive interference in thin films suggests that one of the reflected waves has undergone half-cycle phase shift. Such a phase shift can be predicted from Maxwell's equations and the electromagnetic wave nature of light. So the details of this derivation are beyond our scope, but there is a result. Suppose a light with electric field amplitude EI for incident wave that travels in an optical material with index of refraction, let's say NA. Okay, so NA here. And strikes at normal incidence on an interface with another optical material with an index of refraction NB. Okay. The amplitude of the wave reflected from the surface, let's call it E reflected, can be shown that equals NA minus NB over NA plus NB times amplitude of the incident wave or normal incidence, and this is for normal incidence. Well, what can we say about this result? We can say the result shows us that incident and reflected amplitudes have the same sign if, so let me write that, same ER and EI have same signs when NA is greater than NB, and they have opposite signs when NA is less than NB. Well, because amplitudes must always be positive or zero, a negative value means that the wave actually undergoes a half a cycle, which is 180 degrees phase shift. Well, there are three different possibilities that we can discuss. So let's start with the first case, where NA is greater than NB. Second possibility is where NA equals NB. And finally, the third possibility is when NA is less than NB. When a light of a single wave is incident on the interface between these two materials, so as we said earlier, some of it will reflect and some of it will transmit through. And since NA and NB have NA is greater than NB, so EI and ER have the same sign, so there is no phase change. So reflected ray has not undergone any phase change, so no phase change here. If I attempt to draw this as a wave, so you can see here's the wave comes, sinusoidal wave. Okay, so reflection, so they are in phase. Okay. Now let's try the second part of this. When the NA equals NB, there is pretty much no reflection. The light is gonna be incident and transmit through. So no reflection here at all, and the light is gonna go as it is without anything, just passes through. And it's let me just mention that here, no phase change. Actually there is no reflection for a phase change, so let's just write here no reflection. And this light is transmitted. Finally, the next case, when you have again the light is incident, and then some of it reflects and some of it transmits, and we know that the transmitted ray, reflected ray here undergoes phase change because NA is less than NB. That's right. This is our reflected ray, and it undergoes a phase shift of pi radians, or 180 degrees, or you could say half cycle. Now for case 3, where NA is less than NB, so the light is incident from the lower index of refraction to higher index of refraction, there is a phase shift of pi radians or half cycle. So reflected ray, reflected ray is wave is actually shifted by half a cycle. So to better picture the situation, let's actually do some examples of thin film on thin gasoline on a water. Okay, suppose we have a thin film with the thickness T, and it is on the top of a water. So here we have a gasoline N gasoline equals 1.40, and we have it's on the top of the water, and water, let's just use a different color here so we know it's a water. And the light is incident, it travels from the air, so which means we have on the upper surface of the film is connected to air, so N air, which equals 1.00. And water is 1.33. Okay, now the incident wave travels from the air to the interface of the air gasoline. Some of it transmits and meets the gas and water interface, and some of it reflects. First, let's take a look at the interface of air and gasoline. So because the N air is less than N gasoline, that means we will experience a phase shift, half a cycle. Okay, so let's put 1/2 lambda. So which means if the incident ray is going this way, okay, so we will get a reflected ray. Let me use a different color here. So it will be going undergo phase change. Okay, and then let's take a look what happens to the transmitted ray. So the transmitted ray is going to continue and it's going to meet the gas-water interface. So what we have here, we have N gasoline is greater than N water, which means we will experience no phase shift. So 0 phase shift, right? Now this wave will reflect from its surface, from the surface interface between interface of gas and water. Okay, and some of it will pass through. This wave without a phase change, let me just draw that without phase change, which means we will get something like this. A little bit off. Now the light reflected from the water gas interface strikes the gas air interface where the N gas now is greater than N air, so which means there is no phase change again or shift. So let's put a 0 here. So the net phase change can be added, all the phase changes together. Net phase change will be all these added together. So it's a 1/2 lambda plus 0 phase change. That is a 1/2 lambda. Now for destructive interference to happen, we want the path length difference, like two waves go path, their path length is the R2 minus R1. If this is your first wave, this is your second wave. So the first one has gone a distance like from here to here, and the second one goes a distance that is going through the thickness 1t and then 2t and extra 1. So the difference would be extra 2t distance. Let me write it here, t and then t here. So then it would be 2t, the difference between the path lengths of these two waves. Now, for the destructive interference, as we started talking about, so destructive, the condition is delta R should equal m plus 1/2 lambda, where m equals 0, 1, 2, and so on. Now, for this one, I'm going to write a 2t plus the phase change that we have, okay, 1/2 wavelength should equal m plus 1/2 lambda. So if we simplify this equation, we will get 2t equals m lambda. So this would be, for a thin film, 2t equals m lambda will be the destructive interference. And similar analysis will bring us to t equals m plus 1/2 lambda for constructive interference. Now let's discuss another situation where the gasoline is on the top of glass instead of the water, where the index of refraction of glass is 1.52, and then gasoline is our thin film that has a thickness of T. Okay, so let's try to construct the same situation. We have a light is traveling through the air first, incident to the air-gas interface, and it's going to reflect first wave, and there is a, I'm gonna just write immediately because we saw there is a phase change, 180 degrees phase shift, which is half a lambda cycle. And then some part of this incident light will be transmitted through the gasoline and hit the surface of the gasoline and glass. Well, look at this. The glass's index of refraction is greater than gasoline, so we have a phase change happening here as well. So let's just go ahead and draw our reflected ray this way, and then some will pass through. I'm gonna just have a phase change here, phase shift for this guy right here, and then phase shift in here, okay, which is again half a lambda, which is half a cycle. And then the ray is reflected ray wave is incident to gasoline air interface, so it travels from gas to air, which means goes from higher index of refraction to lower index of refraction. That means we have no phase change. So this is my second wave, and my second wave, I'm gonna have no phase change. Now, total phase change in this case will equal Okay, so we have 1/2 lambda here, 1/2 lambda here, and 0 in here. So that would be 1/2 lambda plus 1/2 lambda plus 0 equals lambda, which is a total complete cycle, which means 0 net phase change. So if I want to write net phase change equals 0. In this case, though, for the destructive interference, okay, so again we have a destructive interference condition, delta R equals m plus 1/2 lambda. Let's identify destructive, and this time my delta R is 2t only. It just goes one distance t and then 2t. By the way, so this is an exaggerated picture, so it's the path length, because remember this is a very, very thin layer of gasoline. So 2t equals m plus 1/2 lambda. So in fact we want to just write 2t plus 0 phase change. So pretty much you have the path, the distance that a wave traveled, extra 2t distance here, traveled extra distance, the second wave, and no net phase change, no net phase shift. Okay, so that would be, in this particular case, this would be for the destructive interference. Okay, for the constructive interference, similar analysis will give us 2t equals m lambda for constructive. As you can see, in every case it is different, and it is all about the phase shift, finding the total net phase shift in this situation. Another method for observing interference in light waves is the Newton's ring. So please stay tuned for the next video on Newton's ring. Thanks for watching.